Hello there, everyone. This is a video on section 4.4 graphing linear inequalities. And this is a lot like graphing a line, except for we're going to be dealing with inequalities, which means not necessarily equal to. So let's do a quick review of what inequality symbols there are. So some people use an alligator or a Pac-Man. I think about the size of the side that it's on, but it's really important, remember, no matter how you remember these things, is that you remember them. So it might be helpful to write this down. This inequality, as we read it from left to right, we would say less than. Now, we can say other words than less, like smaller than, but it is that the number on the left is smaller than the number that is on the right, or value. Vice versa, the second one would be greater than. Again, as we read it from left to right, we have the bigger side on the left and the smaller side on the right. These next two are extremely similar to the ones above. If you notice, this symbol goes exactly the same direction as that one. So this is still less than, but that line underneath it means it could be equal to. Hey, and last but not least, very similarly, this is greater than or equal to. Now, what those just mean is that it is possible for the two sides to have the same exact value and for that inequality to still be true. So let's think about these next problems and how that works. So if I have number one, I have 11 equals to 2 times 4 plus 3. Well, that will be 8 plus 3, which is 11 equal to 11, which is in fact true. Those two things are equal to each other. In the second one, I have 2 times 5, or 10, plus 3, which would mean I have this inequality. We would say this out loud as 10 is greater than 13. Well, 10 is not bigger than 13, so this would not be true. In the next one, we have 10 is less than 13. This is true. 10 is smaller than 13, so that would be a true statement. The next one, we have that negative 5, and we end up getting negative 10 plus 3. Well, negative 10 plus 3 is negative 7. Sometimes this gets confusing with negative signs, but we would read that symbol. Negative 5 is less than or equal to negative 7. Negative 5 is actually bigger than negative 7 because it is less negative. So that is false. And then for our last one here, we have negative 3 is greater than or equal to negative 3. Now, if this did not have that line underneath it, this would be false. But because we have that equal to line here, this is in fact true. Those two sides can be the same. A look at how this impacts us when we're graphing a linear inequality. So if you look at the example, I have y is greater than 3/4 x minus 2. Now, the best thing about this today is we are going to keep all of our linear inequalities in slope-intercept form. So that means our step one is to just plot like we normally would the y-intercept and the slope, just like we normally would. So in this problem, my y-intercept is negative 2 and my slope is 3/4. So I would start down 2 and then I would go up 3 and to the right 4 since I have positive numbers for both. Now I'm going to keep plotting some points because I am not very great at drawing straight lines. You would be fine if you just stuck with those couple points. Now, before I connect these points with a line, we need to think about that inequality sign. Step two is to connect the points with a line, but the type of line we use matters. So we have a couple different categories of inequalities. We have the inequalities where there is the equal to line underneath it, and we have the inequalities where it cannot be equal. If we can be equal to, that means we have solutions on the line. All of those points that we have 3 is less than or equal to 3, all of those are just fine. So in that case, we use a solid line to represent it. So just like we would normally graph a line. However, when we do not have that equal to line, we have to use what's called a dashed line, or some people call it a dotted line, because all of those values on that line don't actually work. You can't be equal to them. So in our case, because we have this symbol, we are going to use a dashed line. This is the thing that I always mess up because I go way too fast and I forget to think about it. So make sure you're pausing and thinking about what kind of line you are going to draw. Now, if this was my final answer, I would really have no solutions because that line doesn't really exist. There's not solutions there, but I know that there's points that I can plug in here to make it work. And I know in fact there's infinite points. So I need to find or represent where those solutions are at, those infinite solutions to this inequality. And this is where we're going to use shading. There are different ways of shading. However, in my experience, there are some ways that are easier than others. Again, we're going to go back to some categories of inequalities that we have. These types of inequalities are similar because these two are both more than, and these two are both less than. When we are more than something, we are above it, we are bigger than, we are higher than. So we are going to shade above the line. If we are less than something, we are smaller, we are below. So we are going to shade below the line. Again, there are other ways of shading or thinking about it. However, I think this is a really great way to think about it. When you're trying to decide, you're going to look at what this symbol is. So ours is read as greater than, which means I am going to shade above the line. Right. So above the line, what I typically do is I look at my y-intercept and I find all the points that are above that line. That's where I'm going to be shading. And it's not just the y-axis that I shade, but it is the whole grid above that line. And you can kind of get creative here and scribble and do all that kind of fun stuff. What this means is that any point that is in this shaded region, let's say I use this one. I like that one. It's really easy because the coordinates are 1, 1. If I were to test that point, in other words, if I were to plug that point in to this inequality, so I'm going to plug in 1 for y and 1 for x, I would get a true statement. I would have 1 is greater than negative 1.25, I think is what it ends up being. And 1 is in fact greater than that. I could test all of the points in there, but I don't really want to do that. So I'm just trusting my shading to represent the fact that any point in that blue region is a solution. Now, the points that are on the line, oh, it will not write. The points that are on the line, because it is dashed, are not solutions, but anything in the shaded region would be. I hope that helps. Have a great day.